Our last example of work presents us with something that's pretty different than what we've been doing in this series of videos. A circular swimming pool has a diameter of 24 feet, sides that are 5 feet high, and is filled with water to a depth of 4 feet. The question is, how much work is required to pump all the water out over the side? Well, here's our pool, and this is going to take a little bit of thought. If I'm going to pump this water out over the side, a way to think about what is happening is that we're taking just the top layer of water and removing it over the side. And if I remove layer after layer after layer, then the size of the layers in this case isn't changing. It's based on the area of a circle. But the distance that the layer is moving changes. So let's say we're considering this pink layer of water somewhere within the water. This pink layer has a depth. Let's say it's got an incremental depth that's delta x. We could do this in terms of y, but x is, I think, more comfortable. And this layer of water has an area. In this case, it's going to be 144 pi because our pool has a diameter of 24 feet, and so a radius of 12 feet, and the area of a circle is pi r squared. So the volume, so I'll call this an incremental volume, of this layer of water is 144 pi times delta x. We're told the density of water, 62.5 pounds per cubic foot. And so the weight of this layer of water, I don't want to use W because we're going to use that for work, is 62.5 pounds times 144 pi times delta x. Since this pool is circular with vertical sides, all the layers of water have this weight, which, as it turns out, is 9,000 pi times delta x. Weight, by the way, is another name for force. And so we can say like F of x is equal to 9,000 pi delta x. Now let's talk about what's going on when we pump out this layer. When this layer gets pumped out, I don't know how far down this layer is, but let's say from the top edge of the pool, this layer is x feet. That x feet is the distance that that layer has to move to go over the edge of the pool. As the water is pumped out, x is increasing because the lower the level of the water is, the higher, right, or the more distance that layer has to move to be pumped out of the pool. So let's see if we can turn this into a mathematical expression. I bet we can. The work is going to be equal to an integral. I'll just write the limits from a to b, and we'll talk about what they are in just a minute. You know what, I'm going to leave them blank, and we're going to fill them in with actual numbers. Now remember that work is equal to force times distance, but in this case, we're going to write it as work is equal to distance times force, just because of what we've already developed. The distance that a layer of water is going to move, in this case, is going to be x. The force that's being moved is the weight of a layer of water, which we've already decided is 9,000 pi times delta x. You know, limit is the number of layers goes to infinity. Our integral is the integral of x times 9,000 pi dx. Now, we're integrating with respect to x. What did x represent? The distance that a layer of water has to move. In this picture here, the pool is 5 feet deep with water that's 4 feet deep. At minimum, this very top layer of water needs to be raised 1 foot to go over the edge. At maximum, this very bottom layer of water needs to be moved 5 feet to be pumped out over the edge. Therefore, my limits of integration are from 1 to 5. As we've seen, the actual calculus here is pretty straightforward. 4,500 pi x squared for x going from 1 to 5. And this result is 108,000 times pi foot-pounds or approximately 339,292 foot-pounds, whichever makes more sense to you to report. This generalizes to become that the work required to pump water or fluid, out of a container is W is equal to an integral from A to B of h of x times delta A of x dx, where delta is the density of the fluid, A of x is the surface area of the fluid, and h of x is the distance or height that a layer of the fluid has to be raised in order to exit the container. Now notice, as we said here, the weight of the fluid, of a layer of fluid, didn't change. What changed was the distance that the fluid needed to travel. And so if we look back to what we had been doing earlier, we said that to compress a spring or to lift a cable, we had a variable force, kx, and then we had an incremental distance dx. And the force was changing, that's a variable force. In this case, we have a constant force, and it's the distance that's varying, and that's why we need an integral. We could have a slightly more exotic situation. We could have a tank whose sides aren't vertical, and therefore the area of a layer of water would be changing with the depth. We can have a spout so that we'd have to raise a layer of water some distance plus the distance of the spout. But all of that is wrapped up into this formula here. And that can make for challenging situations, but if you know what these pieces represent, the h of x and the a of x, then you should be in pretty good shape.